Hello everyone, I'm Anirudh and I'm here to present our work on how to use inaccurate models for planning and execution with provable guarantees. With access to accurate models, we can achieve successful planning and execution like in this example, where PR2 objective is to pick up this light object from the start location and move it to the goal location while avoiding the collision with the obstacle. If we have an accurate dynamical model that captures the weight of the object, the location of the obstacle, and other relevant parameters exactly, then our planner comes up with a path that avoids the obstacle and our execution is successful. However, what if the object to be picked up is heavy in reality? In other words, what if the dynamical model was inaccurate? Since the object is modeled as light, the planner comes up with the same plan like before. However, upon executing it, the robot cannot lift the object beyond a certain height as its joint torque limits are met, and the arm is stuck. Thus, our execution fails due to the inaccuracy of the model. Our objective in this work is to come up with an approach which provably guarantees that the robot will reach the goal online despite using an inaccurate dynamical model. We consider the reset free setting where the robot has no ability to reset to a particular state and hence needs to reason online. This can be formulated as a shortest path problem consisting of a cost function C that maps any transition to a bounded cost between 0 and 1, and the unknown true deterministic dynamics function F that maps any transition to its successive state. For the purposes of our work, we assume that we have access to an approximate dynamical model F hat that predicts the successor state for any transition. To quantify the inaccuracy of our approximate dynamical model, we introduce the notion of an incorrect transition, which is any transition where F and F hat differ. Let's take a look at how this problem is tackled in existing literature. On the left of the spectrum of existing approaches, we have works like Dyna that update the approximate dynamics using online executions. On the right, we have model-based reinforcement learning works that learn a new dynamical model from scratch purely from online executions. And in the middle, there are residual approaches that learn a residual dynamical model to compensate for the inaccuracies of the approximate model. Our approach, CMAX, also lies in the middle of the spectrum, but unlike all of these works, CMAX does not learn or update the dynamics and is heavily goal-driven. The idea of CMAX is very simple. During online execution, while the current state is not a goal, CMAX plans a path from the current state to the goal using the approximate dynamical model. It then proceeds to execute the planned action online. If we notice a discrepancy in the dynamics, or in other words, the transition was incorrect, then we simply inflate the cost of the executed transition to a large value, thereby forcing the planner to avoid using this transition unless there is no other choice. Subsequently, we move on to the next time step and repeat. Crucially, it is very important to notice that CMAX never updates the approximate dynamical model F hat and does not seek to learn the true dynamics. It only tries to reach the goal while avoiding regions where the approximate model is inaccurate. We can provably show that CMAX is guaranteed to reach a goal state. It takes a number of steps that is proportional to the number of states and number of incorrect transitions in the worst case. In other words, CMAX is complete. Our work also presents a practical instantiation of CMAX designed for extremely large state spaces where instead of planning all the way to the goal, we use a limited expansion search-based planner that uses fixed amount of computation leading to a real-time operation. We also employ global function approximation techniques to maintain the value function to achieve generalization in state space. In addition, we also employ local function approximation techniques to maintain the set of discovered incorrect transitions. Specific details can be found in the paper. Let us revisit our motivating example and see how CMAX operates. With the heavy object and the inaccurate model, CMAX quickly discovers the regions of state action space where the model is inaccurate and adapts the planner to avoid those regions. This results in CMAX quickly discovering a path that takes the object behind the obstacle to the goal location successfully. We have also compared CMAX to baselines on simulated tasks. On the left, we show how CMAX performs in a simulated 4D planar pushing task, where it takes substantially less number of steps when compared to a model-free approach and approaches which learn a residual model online using both global and local function approximators. CMAX also obtains a significantly higher success rate compared to these baselines. On the right, we show CMAX performance in a 7D arm planning task where it outperforms a planning baseline that updates the approximate model online with a substantially higher success rate. I would like to conclude with our result that we can achieve successful goal-oriented execution using inaccurate dynamical models without ever learning the true dynamics. Thank you.